Line P1, we're taking a look at learning task number 14, where we are going to go and describe instrument transformers. First of all, the term instrument transformer is still utilized in the same way that any other transformer does. What it is going to do is it's going to go and reflect changes on one side over to the other side. But what an instrument transformer is going to do is it is going to do so incredibly accurately, with the point being made that they're accurate enough that we can use them for revenue metering, or in other words, for billing people on what they have. Oftentimes what we'll have is we will have large services that are going to be coming into a building, and those large services might go and have, we'll put in here a 600 amp service. Okay, I've got 600 amp conductors that are going through my main fuses and disconnect inside of here. From there, I'm going to go and feed out. What would be really difficult for BC Hydro to be able to do would be put in an inline meter. The same as those meter bases you see on the side of the house. You got that socket, that gray box that has got the round hole on the front there that you plug the meter into. Those things are rated to no more than 200 amps, those actual meters that go and plug into them. Because if they go into a meter that's going to be able to directly carry through 400 or 600 amps, they would need to have incredibly large meters. They'd be super bulky, they would also be very expensive, and they would be non-standardized. What Hydro has done, and most power utilities worldwide have done, is they have standardized on a single type of meter. And that means that they can carry around a bunch of those on their work trucks, and if there's a problem, they just grab one out of the work van and replace it. With whatever the other one was. But in order to do that, they would have to have a way to take this large amount of current, this 600 amps, down to a smaller amount of current, never any more than 200 amps. What they'll actually do is they'll take it even smaller. Because they can. They don't need to necessarily go smaller, but the smaller you go, the less problems you have for the amount of power you could have underneath an arc. The safer it's going to be for your meter technicians. And BC Hydro is really all about safety. They have safety meetings all the time. Part of every day is going to be going over top of safety and the safety concerns on every job. Most of you should be doing the same as well, but you don't. Some of you just kind of roll in with a cup of coffee and just go straight to work without assessing safety. And you're fine 90% of the time, but you do get those accidents that sometimes could be prevented. Hydro does not want to go and have that, so they're going to go and operate safely, but they're also going to go and mandate safety. And part of that safety is going to be the use of instrument transformers that are going to go and drop us from either high values of voltage coming in or high values of current down to smaller, manageable values. The values we see province-wide are going to be 120 volts. They will take from any larger voltage. It could be 600 volts. It could be 12 kV. It could be, even 240 volts. They'll drop that down into 120 volts inside, or they just actually don't connect to any of the lines. But whatever your values of voltage are that you are going to be feeding in, they are going to go and drop those down into 120 volts. Same with anything for my currents. If I've got current, I'm going to always drop that down into 5 amps. This is going to be any current that is going to be greater than 200. So up to 200 amps, we're going to be cool. But past 200 amps, once we get 400 amps, 800 amps, 1200 amps, whatever those are going to go and be, they're always going to drop those down into 5 amps. Now they're not cutting off the customer. This is not like that. They're saying, well, you as a customer don't get more than 5 amps. What they're going to do is they're going to go and have a sliding scale through the use of instrument transformers, so that as the customer varies from 0 to 1200 amps, in the case of a 1200 amp service, they would be varying from 0 to 5 amps, and they would be able to directly reflect that across, and then they just do the math. If they have got 0 on theirs, therefore the customer must have 0. If they have got 5 on theirs, therefore the customer must have 1200. If they've got 2.5 on theirs, the customer must have half of their regular amount, which would be 600 amps that they would be pulling at that point. So they're able to go and use these as a sliding type of scale, but it's a safe sliding scale. The two main ones that we are going to have are going to be our CTs and our PTs, also sometimes referred to as VTs. Let's start with the CT. The CT has a single primary winding. We are going to go and take all of our current in here. We are going to take all of our current back out over here. In other words, this is going to be a single bar that is going to go and carry through to our load. And then what we do is we wrap a whole pile of turns around it. We know that number of turns on the primary over top of number of turns on the secondary is going to be inverse to my current on the secondary over top of my current on the primary that we are going to go and have, right? We reverse these things back and forth. So what we're seeing is if we want to have a low value of current, then I'm going to need to go and have a high value of turns off of these. It's just simple transformer theory. What they'll do is they'll put a lot of windings together. Now, when we put a lot of windings together, that does mean that we can go and get some high values of voltage that are going to be across these. They are going to be designed to go and give us 5 amperes. This doesn't mean that they're limited to 5 amperes. They can actually go higher than the 5 amps, but they're going to be designed around this 5 amp class. Sometimes Hydro will, in their designs, put these things in and give you something that's like going to be a 400-5 transformer when you've got a 600 amp service. Don't worry, they've done the math. They understand that they're going to be more than the 5 amps, and that's fine. The transformer is able to actually do it. But the nominal rating is going to be 5 amperes. They are a specialized build on these ones. That specialized build is going to go and give them a core that is going to be a high permeability. So it's going to be able to hold on to all of the magnetic lines of flux. And they're going to go and have a really low amount of flux density. They don't want to have, lots of flux inside of that thing that it's going to take a lot of work for it to go and magnetize. So they try to build a fairly large core inside of there. And they do have sometimes a little bit higher number of turns than what it actually, would calculate out to be. And that's just to go and minimize any IR drops, any volt drops that we would have inside of there. They're also going to be ranked upon their accuracy. We've got classes that are going to be a 0.3%. This is not 3%. This is 0.3%. So it's less than 1%. 0.3, we're going to have 0.6%. And then we're going to go and have 1.2%. Obviously, the more accurate that you make something, the more fine-tuned your manufacturing has to be, which comes at additional expense. So these ones over here are going to be more expensive meters, but they're also going to be what we refer to as revenue class meters over here. Revenue class meters just means that they're accurate enough, between 0.3 to 0.6% of your hydro bill is really not going to be that much. Big, massive installations, are going to see a difference, but we are not necessarily going to. Okay, before we proceed further onto CTs, we do need to talk about their inherent danger. And it's this huge issue that lies inside of our industry where people just forget, about some of their basic magnetic principles that have happened in the past, or that you've learned about particularly inside of your first year. What we are going to have is across here, there will always be something that is going to be a meter, right? An ammeter. That's what we're designing this load to go and hook up to, so that it is going to go and drive out anywhere between 5 to 0 amps, based upon the amount of amps that I have got flowing through this over here. The problem with these is, if I remove this, we run into this massive danger where we now no longer have load that is going to go and be on this secondary winding. Which means if we don't have any load, we cannot go and develop any current. And if we can't develop any current, we do not have any counter flux. Really, that's what we're losing over here, is that counter EMF flux that we would go and have. Which means that our transformer core is able to go and drive hard into what was referred to as saturation. We just talked about this in the previous day's materials as well. When we were talking about using the nothing more than that 1-to-2 transformation ratio on high voltage ones, and then we talked about the close transformation on auto transformers with that 240-208, where we drive a core into saturation. It's not usually as bad in the auto transformers because they are generally going to be more coarsely built. They're designed to provide power. They don't have that same high efficiency core. These hydro ones, to get their high efficiencies, do have that. And so what we are going to get is that as we drive current through this over here, remember that my main load, this is hydro coming in and it's going out to my main load somewhere inside of that plant. So us having opened this does not affect what's happening inside of here. Our main load is pulling what's happening over there. That means that there's still going to be current going through, which means that now without that counter EMF, we're going to go and drive our phi, or Webers, our amount of flux, hard into saturation. Saturation is when something magnetic reaches the point where it can no longer hold any other lines of flux. So we see this rapid rise, and then we get to this flat top. This is my flux waveform. And then it stays at that flat rise because it really only needs that amount of voltage. Look, you can just transfer that amount of voltage across here. It only needs a small amount of, not voltage, but current through the primary to go and establish the full amount of flux when we don't have the counter EMF. Because we have that full amount of flux inside of there, right over here, finally, all of a sudden it drops. And when it drops, we see it drops really, really rapidly because it wants to go and rise in the opposite direction. So what I'm seeing over here is I'm seeing a massive change in flux over top of a relatively short change in time. Remember that my flux is directly related to my current. And remember that formula, E is equal to negative L delta I over top of delta T. What is flux? Flux is ampere turns that we are going to go and have, which means that when I get a super, super high change in flux over a relatively short amount of time, I'm going to go and kick out a ridiculously high value of voltage. And that's what they're showing us over here on the bottom. This rapid change in flux is going, and during that change, all of a sudden we're getting this boom, this spike of voltage that's going to come out in the opposite direction over here, 2,000 volts, and then it's going to go and flatten off as my top. As we reach saturation, my flux flattens off, the voltage flattens off. It's going to be low, and then all of a sudden, boom, it's going to go and kick out. What you will see is massive, massive, massive amounts of volts that can get kicked out. Where is this going to go and happen to you as electricians? Generally speaking, it's going to go and happen on your 4 and 600 amp services, because your 4 and 600 amp services are going to be built looking something like this. We'll draw that in over there, and then we will draw this in over here. This is going to go and be a distribution. Electrical panel could be splitters and switches, whatever it's going to be. This is going to be my main incoming switch, and then this is going to be something that's referred to as our metering cabinet. It's where we store all of the CTs. And over top of that metering cabinet is going to go and be a little meter base. Now, the problem is that that little meter base is only tapping off of these windings over here. It's not actually interrupting the main current. But what happens with electricians that have never built one of these, maybe, you get sent to a job site and you're asked to go and work on something, and for whatever reason, you cannot go and access the main switch. Maybe the main switch is inside of a room, the room is locked, you can't get access to the key, but there's an electrical emergency that's going on, and you say, hey, I'm smart, I'll just pull the meter, and then the power cannot get through. There's a massive, massive danger that happens, because what's happening is inside of here, that CT is still in place. It's still passing current through from one side to the other, and my actual CT windings are going around that, and that's what's being fed up and into there to that meter. And so what I'm doing is opening that secondary. I'm not actually interrupting the load itself. You expose yourself as you pull this, you're going to be exposing yourself to these massive, massive voltage spikes, pulling a loaded one. Now, if the service isn't operating, if there's no current going through, if the service is live, there's no current going through, you don't have that danger when you pull it. If the main switch is off, if we were to throw this into the down position over here, then once again, we would have safety in being able to go and pull that thing out. As soon as there's no current passing through this line over here, the CT line, you're safe to pull it out. But if there is current, you stand a chance of just nuking yourself off of that. Be very, very careful. The best way to be careful is to go and short these circuits. Now, I know we don't like that term, short. I'm going to go and use the term bridge from this point forward. The book uses the term short, which is the same thing as bridging them. But bridging just doesn't make us think about all the effects of a short circuit so much. It makes us, think about more of a calculated type of thing. So what I need to do is, before I pull any meter out, I've got my ammeter over here. Before I rip that meter out, what I'm going to do is I'm going to bridge these terminals over here. And at that point, then I can go and disconnect my meter safely, because there's still going to be a path for current to go through. What's the maximum amount of current? 5 amps, because it's all driven off of what we pull through that main bar. Whatever we're pulling, this is my main actual load on the system itself. That main actual load that we have on the system is driving amps through there. Those amps are just going to see a reflection that is going to be anywhere between 0 to 5 amps. This whole winding is rating for 0 to 5 amps. So whether I'm passing that 0 to 5 amps through an ammeter, or whether I'm passing that 0 to 5 amps through a bar, a bridge that's being placed across here, is not going to make any difference. It will not overload it. I don't know if you remember basic meter theory from first year. I'm sure you do, probably. You remember everything. But an ammeter has got a ridiculously low value of resistance. Your ammeter that was in here before really was no different than having a bridging bar across there. There is, right underneath this picture, that big exclamation mark that says, do make sure before you remove it that you short circuit, or that you bridge those secondary terminals and that it is not going to go and cause any problem. Then underneath that, they say some CTs are designed with a special shorting bar that is supposed to short the secondary circuit or the 5 amp circuit anytime that the cover on transformer terminals is removed. Do not depend on it. Make sure that you verify it. They should always be clear, by the way, these little shorting terminals. You'll see them on something like this. I'm jumping a few pictures ahead over here. It's a bar type of current transformer. Very, very common. Sometimes they will look like this, where it's just a single bar in. We will bolt our incoming lugs onto here. We will bolt our outgoing lugs onto there. Other times, what it'll look like this, but it'll be kind of like double wide. I can sort of draw that over top, and it's going to go and have 2 bars that are going to be on it. For a single phase installation, and what we would do is we would feed line 1 into one bar, line 2 feeds into the other bar and back out. Whether it's going to be a single bar type or whether it's going to be a double bar type, what we should see on the side of them is this. This is a clear little window. Inside of here, this is where I'm going to have that 5 amp terminals. So my actual meter is going to go and get connected through to here, the actual ammeter. When I remove this case, what should happen is there's a little bar inside of there, a little spring-loaded bar that should then bridge across those 2 terminals. So I can remove this. When I remove that, I can access the screws to go and pull these wires out from underneath it. It should always, always, always be a clear thing so you can actually see what's going on inside of there. Let's talk about our different types, by the way. We do have wound types of CTs, which are going to go and have a primary winding. That's going to be my main load current. You'll sometimes hear that thing referred to as the load winding instead of just the primary. That's because that's what's driving out to our load. We take the power in, we drive it out to our load, and then we're going to go and have the secondary winding, which is sometimes just going to be called the metering winding. That we have. That metering winding is going to be many turns of fine wire because it's carrying no more than 5 amps. The load winding is going to be whatever our conductors are. We can go and pass these things through here, multiple times through. And as we pass them through multiple times, every time we do that, we increase the amount of flux going through in a given direction, which increases the amount that we will pick up on our secondary side over here. Wound types where we are actually doing the windings ourselves, pretty rare. As components of equipment, there's lots of them out there. What we are more likely to see is going to be either these, which are going to be referred to as window types of CTs. These types of CTs are going to be free floating. It's going to be a big black plastic thing. I don't think I've ever seen any color other than black plastic. That's got a toroid transformer inside of there, so that donut-shaped transformer. The plastic case around here is just going to protect that, and then it's got 2 terminals over here that we are going to go and hang on to there. And what we do is when we install our metering inside of that CT cabinet, we would actually have to run our conductors through the window. And as we run the conductor through the window, we're therefore able to pick up its magnetic type of flux. The issues with these ones is that we're supposed to keep them centered. If they're off-center, we can have some problems with them. If we grab the wrong lines and put them through there, we can have some problems with them. And we need to have these things early on so that we can actually pass our conductors through them. The other more common type is going to be the bar type. You will see these in most of your single-phase services that BC Hydro is going to supply for you. If it is a large service, you might have the single bar. If it is going to be a smaller service, you are going to go and get one of those double bar types. We drew that one out earlier. I erased that all at this point, but it's going to have 2 bars. I'm looking at it from the top. Always looks like this, the double bar type. When you get these, by the way, they do not have lugs bolted onto them. They've just got bolt holes. You're going to have to go and bolt lugs on using your proper torque wrench, of course, so that you get to the correct torque. You guys should not be eyeballing this. Okay? And, professionals, act like it. Buy yourself a $12 Mastercraft torque wrench, one of the manual ones, and use it on those things because there's a lot of expansion and contraction. But you will be bolting in. You'll be carrying your line 1 through one of these. You'll be carrying your line 2 through the other one, and then it goes out to your actual loads. And inside of this whole block, they're going to go and have all the windings that go around each of those bars. But the bars themselves are just a big, solid piece of usually copper that's going to be nickel flashed. All right, our next type of transformer that we have is going to be my PT. It is also commonly known as a VT, or a voltage type of transformer. They are going to go and have many turns on the high voltage side. The high voltage is what we're going to be stepping down, and we're always stepping down to a value in our province of 120 volts. We do not have to carry a lot of power through them, we only need to carry a little bit. So the VA ratings of them are going to be 100 VA to maybe 500-ish VA. Well, it's about the size of a doorbell transformer, a bit larger than a doorbell transformer, but it's going to be much larger on the casing. So the actual windings inside are very small. The casing itself is going to be ruggedized because they're going to be epoxy coating these things. You know, they want them to be tamper-proof and bulletproof because they're going to be in operation for long periods of time. If I need to use one of these to measure something that's going to be large, you know, particularly large values of voltage, most of the time they're going to be done through these as isolations. We are not going to go and have these used as a lot of auto transformers, but even in an isolation, if I go to too high of a value of voltage, it can get ridiculously hard for me to go and measure that. What I'll do at that point is I'll put on a capacitive voltage divisor. I'm just going to go and white this out just for a second so we can examine the cap divider over here. If I have gone, we'll put this one here, we'll put that at 0 volts, and if this is at 12 kV right now, what I'm going to have is if I've got equal sizes of capacitor, they would need to be absolutely equal. What I would do then is I would have equal sized plates, which would mean I would drive equal amounts of electrons to each one, and therefore I would have an equal value of voltage that I would have over top of each one of these, right? Going back into your basic capacitor, theory, V, Q, C, all of that. So what we can do is we can take equally sized capacitors. A capacitor is lovely because a capacitor is really just a insulator, right? We got dielectric in between. These are going to be heavy-duty ceramic types of caps over there, but we are insulating this ground, or this line is never actually touching down to this line over here because that cap is just a plate with insulation in between. So we got 5 layers of insulation over here, but it's going to be controlled insulation. What we'll do then, if we got 5 of these, we just divide that value by the number of caps, and it tells us the total number of volts that we have over top of each section. We'll take 12,000 divided by 5 gets us to 2,400. So each of these caps is now going to be 2,400 that we're going to see across it. What do I see over here? I see that my PT is going across 2,400 plus another 2,400 over here. So it's going across 4,800. So this means that I'm only doing a voltage transformation of 4,800 down to 120 volts off of it. It's just easier to go and build these things for that smaller, the insulation is really where it breaks down inside of these things, right? So it's easier to build it for 4,800 to 120 rather than having to go to 12 kilovolts to 120. Last thing that we have to talk about on our PTs is just going to be that they are all polarity sensitive and they are all polarity regulated, which means that they're going to have dots on them. We do not necessarily have the H's and X's. If they do have an H, it is oftentimes going to just say H on one side, X on the other, but they're not going to use the 1s and 2s. They will use these dots. And what we need to do is we just need to connect the dots later on when we do our connections, make sure that they're all aligned together. We'll do that inside of our next learning task where we'll take a look at the connections and the readings that we will have off of them. Here's my CT. Here's its polarity dots as well. All right, that's it for the basic layout on what a instrument transformer is. Remember, a PT is going to be rated for 120 on the secondary. A CT is going to be rated for 5 amps.